So next I want to explain to you how we model field accesses with pushdown systems and how we do this in synchronized pushdown systems. So just to recap, so what we want to avoid is this blow up in the length of access paths in recursive data structure unrolling like we see it here, because this blow up leads to the fact that we need to artificially bound this using k-limiting. And yeah, that will basically prevent us from getting good precision because we will need to approximate, and yeah, we don't really want that. So the alternative is here that we will use a pushdown system, and this is actually going to be a sort of second pushdown system because we will also be modeling calls and returns using a pushdown system, like I already explained, for context-sensitive analysis. But here we will have a second pushdown system, the pushdown system of fields. And yeah, I want to explain to you how this works using this simple example. So let us assume that here we are tracking this particular object that has been assigned to C, so object 03 at line 3. And we're tracking this through the program. And on the right-hand side, you will see our post* automaton that we are building for this example. So at the beginning, variable C is pointing to this object, so the automaton looks like this. So we have C with an empty field access expression that is actually pointing to object 03. Then when we process line 4, we will actually be using a push rule, because here at line 4, we are actually using a field access A, so we are storing something to the heap, right? And this field access expression, and in theory, it could be arbitrarily long, right? But here it's just a single field, and so that's why we are pushing this onto the stack. And then for every further field access, that's the idea, we would be pushing further and further onto the stack. And you have seen push rules before. This is similar to what we have seen before, except that here we are now pushing not call frames, but we're actually pushing fields. So here, this is saying p.a is now pointing to whatever C was pointing to earlier, okay? And other than that, the push rule is simply as what we have seen before. So here, p with a will actually bring you to the same object that C is also pointing to. And then the access paths that we normally saw, they're basically represented through a regular expression or a regular automaton that is formed by this post* automaton. In this example, you will also see that in line 5, we have to use a pop rule, because here we actually have a field load. So this now means that D is pointing to whatever p.a was pointing to earlier, and we can encode this using a pop rule. Like you see here. So this is basically saying we have something that p.a points to, and if we ignore that field A, so if we pop it away, so that basically gives us only D, and then D is pointing to the same thing. That's the encoding that we use, and in the automaton it will then be represented as you can see here. Okay. Now, the interesting question is, of course, how does this help us with the recursive unrolling example that we saw earlier? And the hope here would be that we now gain a finite representation for this infinite number of access paths, right? And so now let's assume at the beginning again that we are at line 3, and so C is pointing to this object 03. And now I've also made explicit that variable p is pointing to this other object that has been allocated at line 2. Okay. Next, we are processing line 5, and we are again generating this push rule that I showed you earlier. So we are connecting p.a, so to say, to the object that is pointed to by C. Next, we are processing this line, so C is actually pointing to the same object that P is pointing to, so we will introduce such an edge here formed by the appropriate rule. And now the interesting thing comes, now we will wrap around the loop. right? And so when we wrap around the loop, you will see that this will cause us to actually reach a fixed point after the next step. So we will now process this particular statement here again. And now this is again saying P.A points to whatever C points to. But previously we have learned that due to this assignment, C can actually also point to O2. So this means that for P.A, we now also have an edge that leads to O2 here. And now implicitly, this will encode all the different loop unrollings that you can have, because from P.A you get to O, but from P you also get to O, right? And so this means you can infinitely often unroll this and you will always get to the same object. And that's exactly what we meant to encode, right? And now this is a finite encoding. And in particular, we have now reached the fixed point, because if we now were to process this assignment here again, then you would see that nothing actually changes. This post-star automaton saturation has terminated because the automaton has actually been fully saturated. And that's actually really nice, right? So we have now a finite representation to encode a potentially infinite number of different field accesses that can be caused by such a loop. And we obviously can use the same also or the same mechanism to also encode calls and returns. I've also shown that to you already. And this in combination makes the approach really exciting, because then we can precisely model field accesses and we can precisely model calls and returns. And that should give us actually very nice analysis, right? I should say that this way of representing access paths as automata, it's not entirely novel. So there has been a previous approach called access graphs that was trying to do something similar. But we were actually the first to use this kind of modeling through pushdown systems in combination with a second pushdown system that also models calls and returns. And this is work that we actually published in 2019, so that even received a distinguished paper award at our top conference, POPL. This is because we were really able to show that using this kind of modeling, you can really get rid of this necessity that you would otherwise have to actually use k-limiting. So we can get rid of that particular approximation. As I will later show you, though, there's still a bit of approximation that we have to do in some place, but that typically doesn't hurt you very much. I'll explain to you what that looks like and why that is. But why did we get this distinguished paper award in the first place? So the point is that we almost solved a problem that is known to be unsolvable. So why is that the case? Well, we already know that single pushdown systems have been previously used to model context sensitivity, right? So I've already shown that to you in the previous lectures. Then Boomerang actually used this additional second pushdown systems for field sensitivity. And both pushdown systems are actually synchronized using so-called, or yielding a so-called synchronized pushdown system, SPDS. That's what this paper was really about, okay? But the thing is, if you use two pushdown systems, then normally you get something that looks like this. What is this? Have you seen this before? If not, I encourage you to take a look at this link. This is actually a Turing machine built out of Lego. Because using two stack machines, two pushdown systems, one can actually build a Turing machine. This has been proven a long time ago. And in essence, this means that whenever you have two pushdown systems in combination and you let them arbitrarily interact, then you get something that is Turing complete, and therefore it's undecidable. And Thomas Reps, he published a while ago a paper that actually showed that one cannot build an analysis that is fully context sensitive and field sensitive, because that would exactly require such two different pushdown systems, and therefore it's undecidable. Okay, so that's disappointing, right? And that probably also led to the fact that this attempt to combine the two sensitivities, context and field sensitivity, that had been thought to be futile for quite a while, and people didn't really engage in any such combinations. Then you have to see, though, that this is only saying the following, right? So what this is essentially says is that you cannot build an analysis that is fully context sensitive and field sensitive for every program. Okay, that is exactly what is undecidable. But the point is, you do not necessarily need to do that for every program. You only want to be able to do that for programs that people actually analyze. And that's what Johannes Späth was actually be able to show in his PhD thesis, that one can actually build an analysis that is fully context sensitive and field sensitive for all practical purposes, because it's for all programs that people actually write. And so what this is really doing is that it's combining an approach that uses a pushdown system of calls, right, for calling context sensitivity, that gives you flow sensitivity and context sensitivity, with a pushdown system of fields that gives you really flow sensitivity and field sensitivity. Okay, and we're combining all of this, so we gain the best of both worlds. We get something that's to the largest extent flow sensitive and context sensitive and field sensitive. And you can also look into this in terms of set theory. So if we assume that this models the entire possible program behavior, so that's sort of the behavior that a program can expose at runtime, then you can have erroneous or vulnerable behavior like this here, right? So these are all the sort of illegal program states. And ideally, we want to capture exactly those, right, with a static analysis. Now, you can have your program analysis warnings, and typically they will look like this. So if you have a sound analysis, it will capture at least all these erroneous states, but it can also have false positives, right? And it can have false positives that the program can actually expose. So this is a program configuration that can happen at runtime, but it's not actually an erroneous configuration. But you can also get such false positives here that the program cannot even exhibit, because the program can never actually be in this state. Okay, so you can have both kinds of these approximations. And ideally, you want to have such a perfect alignment, right? Ideally, you want to have something that exactly, well, models this erroneous program behavior. But reps basically showed that no such analysis can exist, right? So it's undecidable. You can never have this perfect alignment. Now, what Johannes and I were basically able to show is the following. So if you use one pushdown system, so for instance, your pushdown system of calls, right, it will give you such an approximation. So you will get some false positives. But then if you use a second pushdown system, the pushdown system of fields, now if you use a second pushdown system like you see here, then you will see that this actually models exactly this other ellipse here, right? So you can also get some false positives that you will see here. But the thing is now that if you intersect the two, okay, then this yellow circle in the middle emerges, and you will see that this almost exactly hits or models this circle that we had in the beginning, right? So this almost exactly models the erroneous situations that we are after, except for these little false positives that we see here, right? And there are false positives that are possible in theory, but as I will show you on the next slide, these barely ever happen in practice, or they only typically happen in some obscure situations. And that's probably then good enough for us, right? So let's take a look at such a such a case where this actually can fail, right? So let us assume we have such a program here, right? So it actually calls this Quux method, and Quux is calling bar and bas, which are actually defined here. So bar is calling foo, and bas is calling foo as well. And they all do some different pointer assignments, pointer mumbo jumbo, right? That will come important later as we actually go through this example. Because we could now ask the question, can A and Y actually alias? Okay. And now we want to determine this aliasing relationship by using our two pushdown systems. Okay. And now what you see here is basically a sort of simplified way of encoding these pushdown systems in a single graph. So what you will see here is that we have actually processed the call at line 63. So this is the call to bus, okay, encoded in our call pushdown system. So this is basically a push rule in the call PDS. Similar here, we have a push rule for the call at line 62. In the call PDS, this models the call to bar. And here, these are basically field accesses in bus, these are field accesses in foo, and these are field accesses in bar, okay? And here again, we have a call from bus to foo, and a return from foo to bar to bus. And here we have a call from bar to foo, and a return from foo to bar, okay? And remember that, of course, we can only process at runtime matching calls and returns. So if we call here, we have to return there. Likewise, if we have this call, we need to return there, right? But the other way around, we also need to match pushes and pops from the field PDS, right? So we need to match stores and loads. So that means, for instance, when we have a field write G here. So this is assigning something to P.G in foo and to Q.G, and we can see that in foo, right? So that's happening here. Then this needs to be matched by a corresponding load that we see down here, right? So this is loading the field G in method bar, and we can actually see that up here. And now the question is basically, can we have aliasing between A and Y? So is Y reachable in the graph from A? And now you have to see that in order to get a precise result, you would really need to very closely interact between the call pushdown system and the field pushdown system. But once we do that, we get an undecidable problem. So in the synchronized pushdown systems construction that we presented in the paper, the construction is actually relatively simple. We will basically run both the call PDS and the field PDS side by side. And only at the end will we take a set intersection, basically, right? So we will basically independently answer the question, can we reach Y from A using the call PDS? And then we will answer the question, can we reach Y from A using the field PDS? And if both is true, then we assume that this is actually reachable, so we have some aliasing, okay? But now the problem is as follows. If you look into the program with these different paths that can lead to Y, there are essentially two paths, right? So one is this one here, and one is the one from the top here, okay? Now, if we first take the path on the top, you will see that along this path, actually the field accesses match up nicely, right? So here we are writing to F, we are writing to G, we are reading from G, and we are reading from F. So the field PDS will tell us, nice, this works, right? So it's all matching up. But the call PDS, it does not match up because here we are calling out of call site 67, but we are returning to return site 53. That's not good, right? So the call PDS would actually tell us that this is an unrealizable path at runtime. But because here we are considering both paths in isolation, nonetheless, the field PDS will tell us this is realizable, right? Now, the bad thing here is that if we go along the bottom path, the inverse happens. So at the bottom path, the calls actually match up because here we are calling at line 53 and we are returning to line 53. So along this path, actually the call PDS will tell us, nice, it's all matching up. But this is the case, although here the field accesses don't match up, right? Because here we are actually writing to H and we are loading from G. So there's a mismatch. But again, this doesn't matter because here we are only considering the call PDS. So basically the field PDS is happy along the top path and the call PDS is happy along the bottom path. And because we only combine their results at the very end, we lose some precision here, right? So this means that in this example, and you can actually really implement this in Boomerang and look for yourself, you will see that you will actually get an over approximation, so that Boomerang would actually tell you that after executing this code, A and Y can actually alias, although that is never at runtime actually the case. But you will see that this is a relatively convoluted example, right? It's very constructed. I mean, we constructed this on purpose to illustrate exactly this problem. So the question is actually, how often does this really arise? And if you take a look at our paper, you will see that we were actually unable to find any such instance in the benchmark programs, at least, that we tried. And these were real-world programs that we run this analysis through. So it means, yes, in theory, there is a precision loss, but in practice, we were actually unable to show any practical impact through this theoretical precision loss. And to some extent, this at least empirically shows that we are able to solve this problem that was thought to be unsolvable to a very large extent. What's interesting about this is that also for a long time, people thought that there's an inherent trade-off between performance and precision, right? So you cannot have both. If you want to have a precise analysis, you need to have complex modeling and a complex abstract domain to make it precise, and this will then make your analysis slow. What we were able to show using this work is that this is actually no longer a trade-off, because we here chose a very lean abstraction, right? So like I explained to you, we are only tracking individual pointers. So that makes it a very small abstraction. We can use efficient distributive solvers. So we get something that's actually as precise as it can possibly be. At least I don't know of any more precise modeling compared to what we have here. This is probably as precise as it can get. But at the same time, it's also highly efficient because we're using these distributive frameworks, and they are, they have the most efficient solution algorithms that we actually know of. And so that's interesting, right? Because people thought there's this trade-off. So there were these commercial products that were actually focusing on a high level of precision, but they were actually very slow, right? Because they used these really complex abstract domains. And on the other hand, there were these simple free linters, or basically some off-the-shelf open source tools that were trying to be really fast. So you may have heard of programs such as Findbugs or Spotbugs or PMD that fall into this category. So they use a very simple, often syntactic or interprocedural analysis. And they are horribly imprecise, but they're very fast, right? And people always thought there is this trade-off. So you cannot have both, right? So you will never actually end up in this corner here where you have good precision and good performance. But using this work, we were actually able to show that as you use higher precision, and you use a really highly precise but lean abstraction, you actually get better performance again. So we got a really excellent performance using these techniques that we implemented, but without any loss of precision. And in fact, precision actually went up. So we saw that the analysis is actually much more precise than some previously existing analysis. We were actually able to show that empirically, but at a much smaller cost, right? And that's actually really nice. And we actually implemented this also in some open source prototypes. So I will still be talking about this tool a bit further in later lectures. We have a open source tool called CogniCrypt, which is largely the work by Stefan Krüger, but also Johannes Späth and we contributed to it, and also some collaborators from the Collaborative Research Center Crossing, that is at TU Darmstadt. And by now it's a large open source project that actually a number of people have contributed to, and that these companies here have actually also already successfully used. And internally, this tool is actually using the synchronized pushdown system to actually conduct its analysis. And that's also what makes this tool very nice and precise and efficient. Now, to summarize, what I wanted to explain to you this week is that we built Boomerang as a combination of a demand-driven analysis with two pushdown systems that actually help us implement flow-sensitive pointer analysis. And this all comes together in this approach that we call synchronized pushdown systems. And like I showed you, to a very large extent, the analysis is actually context and field sensitive, right? So it's not fully context and field sensitive because of this counterexample that I showed you. But I also try to explain that these examples are unlikely to actually happen in real-world programs. But this is achieved by sort of synchronizing two pushdown systems, one to correlate field loads and stores, and the other one to correlate calls and returns. And we basically execute both of them side by side and take the intersection in the end when we answer a query. And yeah, this is really what makes this both feasible but nonetheless precise. And yeah, that's all that I wanted to explain to you about Boomerang. And yeah, I'm eager to talk to you about further tools that we developed and that also built on top of this in the upcoming lectures. See you then.